Thank you, David. This is the second lecture on zero sets of Laplace eigenfunctions. 20 years ago, this conference had a problem section, and Nadirashvili, who was leading one of the problem sections, he proposed a plan how to attack Yau's conjecture. He asked two questions on harmonic functions in three-dimensional Euclidean space that were supposed to help to understand the problem of zero sets of Laplace eigenfunctions. And we will be following some of his ideas in higher dimensions. And at the end of this talk, I know that several of you probably heard this talk before, there will be 5% more of new information. We will talk about two-dimensional case, two-dimensional world, which is very nice compared to higher dimensions. And there will be 5% more information about two-dimensional world. Okay, so here we start. Okay, so if you somehow like this subject, I must warn you, it's not easy to find the right ways to start with. I don't know what is the right place to start with, but I personally like the paper of Nazarov, Poltarovich, Sodin. And also we tried to write some lecture notes for this lecture where we give some informal explanation of what is happening in all these problems. And also there are lecture notes from Eugenia's talks at Park City, Utah from this summer. Okay, so now we start. Let me remind you what is Yau's conjecture. So we have a Riemannian manifold. There is no boundary. It's compact and closed. And we look at eigenfunctions. And the question of Yau about zeros of Laplace eigenfunctions, you can see it immediately from the picture. Here is the sign of spherical harmonic of degree 50. And the interface between black and white is the zero set. And Yau conjectured that for any C-infinity smooth Riemannian manifold, the length of the zero set is comparable to square root of lambda. And if you are in not two-dimensional manifold, a higher dimensional, that n minus one dimensional Hausdorff measure is comparable to square root of lambda. Nadirashvili proposed two questions to attack this problem in higher dimensions. I will start with the first of them. Okay, so this question looks quite innocent, but here is the difficulty. So suppose we have the standard Euclidean space, R3, and we look at some non-constant harmonic function. Every non-constant harmonic function has at least one zero. And Nadirashvili asked, is it true that the area of the zero set is infinite? This question is not difficult in dimension 2. So if you have a 0 point of a harmonic function on the plane, we can know that the zero sets of two-dimensional harmonic functions are unions of curves. And any curve is not allowed to have loops. If you have a loop of zero set, then the maximum principle will tell you that the function is zero identically inside of the contour. So any curve would actually be unbounded. It will go to infinity, and there will be a curve, there will be always a curve which has infinite lengths. So in dimension 2, length of the zero set of any harmonic function, non-constant harmonic function, is infinite. And Nadirashvili asked whether the same is true in dimension 3. And the same argument is not working because you can imagine like a very narrow domain which is unbounded. So zero sets of harmonic functions are unbounded, but it does not help. You can imagine a surface which is looking like a needle, a very narrow cusp that goes to infinity. And you can construct such a surface which has a bounded area. But not every set could be a zero set of a harmonic function. In particular, if you know that harmonic function is 0 at the center of the unit ball, then the area of the zero set inside of this ball is at least some constant. And this is a recent result. And if you take this statement and you start rescaling it, if you replace the unit ball by a ball of radius r, the Hausdorff measure is rescaled like r to the power n minus 1. And if you let r go to infinity, you will see that Nadirashvili's conjecture is true. For applications, the rescaled version is more useful. And very soon I will explain to you how the two conjectures are connected to each other. So one conjecture is a question about eigenfunctions. There is a parameter lambda here. And another question is about harmonic function, and there is no lambda there. There is a very nice trick how to pass from, say, Helmholtz equation in Rn to Laplace equation. You add an extra variable t and multiply the solution of the Helmholtz equation by exponent which depends only on the new variable. And you can choose the right constant in the exponent so that the product appears to be a harmonic function in Rn plus 1. So there is some kind of lifting trick that takes a Laplace eigenfunction, you add extra variable, you multiply by exponent, and you get a harmonic function on the product manifold. And the nice thing about this trick that the zero set of a new harmonic function is very closely connected to the zero set of the old function. One is just the cylinder over the zero set of the old function. And if you know something about zero sets of harmonic function, then you can certainly extract some information about zero sets of eigenfunctions. And this trick is working on any Riemannian manifold. Now I will try to torture you a little bit, so I will try to explain why one conjecture implies another conjecture. To be more precise, Nadirashvili's conjecture implies lower bound in Yau's conjecture. For the sake of simplicity, we will talk about the Helmholtz equation in Rn, but the argument is working everywhere. I will try to explain to you why, if we take the unit ball and we take the Helmholtz equation with large lambda, sufficiently large, then the Hausdorff measure of the zero set inside of the unit ball will be bigger than some constant time squared of lambda. We will assume that Nadirashvili's conjecture is true, and we will use it. And we will use also another fact that Eugenia mentioned during the last lecture, that the zero set of eigenfunction is very dense. I take Nadirashvili's conjecture and grant it, and I will just demonstrate how to go to Yau's conjecture from here. Okay, so the density of zero sets tells us that we can actually find many disjoint balls of radius 1 over square root of lambda, so that the eigenfunction is 0 at the centers of these balls, and the number of balls is lambda to the power n over 2. That's what the density tells us. And then we would like just to use Nadirashvili on the scale 1 over square root of lambda. And when we try to use it, okay, we combined it with lifting trick, and there is some rescaling factor here for the lower bound of the zero set. The factor is 1 over square root of lambda to the power n minus 1. It's n minus 1 dimensional Hausdorff measure and is rescaled like 1 over square root of lambda to the power n minus 1. So in each ball, you have a lower bounds. And the number of balls is lambda to the power n over 2. And that's where you gain square root of lambda. Yeah, the argument is working for Riemannian manifolds and shows the connection between two conjectures. Okay, so what about Nadirashvili's conjecture? How do you prove it? So we tried to outline the proof in the lecture notes, and the detailed plan of the proof is 7 pages. I will mention some elements of the proof later, but I will say a few things. The proof of Nadirashvili's conjecture is a multiscale argument. We don't invent new elliptic tools. We just use very classical elliptic things in a clever way. And what does the proof tell us? It tells us a very natural thing, that the faster harmonic function grows, the larger the zero set should be. If you denote the growth of the function by some number n, so here we work with doubling index, you look how the maximum over balls grows when we increase the radius of the ball twice. And if you know that the doubling index is large, if the function is growing sufficiently fast, then you can get good estimates for the area of the zero set, which grow to infinity as growth becomes faster and faster. Before I tell you some things about the proof, I would like to talk a little bit about the upper bounds, because there are several things that appear both in upper bounds and lower bounds. So now, so the statement, the Gauss conjecture, is true for real analytic Riemannian manifolds, and Eugenia explained during the last lecture the beautiful ideas coming from the work of Donnelly and Pfefferman. The idea of holomorphic extension, the idea of doubling index. In the smooth case, we don't have holomorphic extension, but we can prove some polynomial upper bounds. I think about 1 year ago, we were trying to work on the problem in some intermediate case, a case between the real analytic and the smooth case, when you have a bounded domain in Rn with smooth boundary. You have real analytic metric in Rn, but the boundary is not real analytic. And I was giving a talk on this matter, and I was trying to explain the proof, and it was pretty bold decision to explain a proof in 50 minutes of some upper bound for Hausdorff measure of zero sets. And I was trying to explain the upper bound that you see here, the n-1 dimensional Hausdorff measure of the zero set is smaller than square root of lambda, and that time we were talking about some worse bound, square root of lambda times some logarithmic error. And in the middle of the talk, literally, I was stopped by Fedya Nazarov, and he explained me that the proof is over, and why do you need the logarithm lambda? I didn't understand what he was talking, but after lecture, he explained me that there is kind of very simple argument that you can get the sharp upper bound in the case of bounded domains in Rn. Okay, so upper bounds in Yau's conjecture. What do you do here? So again, we would like to use the lifting trick. We add extra variable and consider a harmonic lift. And you can translate the Yau's conjecture into language of harmonic functions. And what you would like is to estimate the Hausdorff measure of the zero set in terms of the growth of the function. So you have a solution of elliptic PDE, and you have the number, the doubling index. It tells you how fast the function is growing. And the harmonic counterpart of Yau's conjecture is that there is a linear bound with a Hausdorff measure of zero set in terms of the growth. And we don't know how to prove that. So the proof of the lower bound and of the polynomial upper bound is a multiscale iteration argument. And I would like to mention one statement which appears in the proof. So in the multiscale argument, it is very frequent that you take a unit cube and you start chopping it into smaller cubes. In the multiscale argument, we play with doubling index, and it is very useful to know how the distribution of the doubling index looks like. And here is a lemma. It states that if you take a unit cube, you assume that the doubling index in this cube is capital N. Then when you start chopping this cube into smaller pieces, then for most of the subcubes, the doubling index will be way smaller. And imagine for a moment that your goal is to estimate zero set in terms of growth, in terms of N. You start chopping a cube into smaller cubes, and you look at zero set in the smaller cubes, and you try to prove the statement, say, in induction by N. And here the lemma tells you that for the most of the cubes, the doubling index is way smaller, twice smaller. And there is a number of exceptions here. So there are some bad cubes where we don't know anything about the doubling index. We don't have the good bound n over 2, but the number of exceptions is small. It's something like 1 over 2 times k to the power n minus 1. And when you try to estimate n minus 1 dimensional Hausdorff measure in iteration argument, it is really important that here the constant 1/2 is smaller than 1. So I was trying to give you intuition where the iterations come from. So we play with the doubling index, we chop cube into smaller cubes, we try to prove some estimates in terms of the doubling index via iterations. Okay, so this lemma is quite useful. Now, I will not going to try to explain the complete proof. The detailed plan of the proof is in the lecture notes. I would like to go over the tools. What do we use in the proof? Some very classical statements. So one thing is our monotonicity of the doubling index. If you have a ball and you consider the doubling index in this ball and you start changing the radius of the ball, then it appears that the doubling index is almost monotone with respect to the radius. If you increase the radius of the ball, the doubling index will become only larger. So there is a word almost here. So it's not really monotonicity, it's almost monotonicity. If you work with, instead of working with L-infinity norms of harmonic functions, if you work with L2 norms, then it will become rigorous monotonicity. So if you take a ball of radius r, if you take the average of u square of the sphere, then these averages, they have some logarithmic convexity properties. And in elliptic PDE, people usually deal with L2 norms. They have wonderful monotonicity formulas, and these monotonicity formulas play a major role. And this is the fact about monotonicity of doubling index. It follows from monotonicity formulas for L2 norms. Please don't read this part of the slides. Okay, we will focus on doubling index. Okay, so what I would like to tell you about the doubling index, so we know that if we slightly increase the ball, the radius of the ball, the doubling index will become larger. In the proof of the lemma on the distribution of the doubling index, so we would like to somehow accumulate the doubling indices. So here is a statement that I tried to formulate informally, and the informal part is what are the blue balls and what are the red balls, but you can think that here is a picture, and here are the blue balls. You have 4 blue balls in 3-dimensional space. You can think that the centers of the balls form an equilateral simplex, and you have a giant red ball that contains all blue balls. And here are the things that if you have 4 blue balls with doubling index at least A, then when you take a giant ball which contains all blue balls, then the doubling index in this ball will appear to be even greater than A. So you can somehow accumulate the doubling indices. And now I will go to another point of view on the monotonicity property of the doubling index. There are several names for this: unique continuation or propagation of smallness. I like this way more. So imagine that you have a harmonic function bounded by 1, and you know that on some set it is extremely small, like say u is smaller than very tiny epsilon in a 4 times smaller ball. Then you can propagate the smallness from this ball to a larger set. If the function is extremely small on some set, you can show that it's still small on a larger set. And this is a property, elliptic property of harmonic functions. And that's why we call it propagation of smallness. You literally propagate smallness from some sets to larger sets. Sometimes you would like to propagate smallness from very small sets, which have 0 volume. And here is one example of such propagation of smallness results. So imagine that you have a domain on a plane. You have a relatively open piece of the boundary, some arc gamma. And you have a harmonic function inside of this domain. And if you know that the harmonic function, the gradient of harmonic function is extremely small on the piece of the boundary, then you can propagate the smallness from this piece of the boundary inside of the domain. And this statement looks like a 3-ball theorem. We really use this this version of the Cauchy uniqueness property for elliptic PD. And I want to say that there is very huge open question here, which was the second question from Nadirashvili's plan to attack this conjecture. We still don't know whether it's true or not, but it apparently would be very helpful. So here is the second question from Nadirashvili's plan to attack Yau's conjecture. This question, it's not due to Nadirashvili, it's many mathematicians asked it, and I think it goes back to at least to Lippmann burrs. So ancient Cauchy uniqueness problem. So suppose you have a unit ball in R3, there is a harmonic function there, which is smooth up to the boundary. So the gradient is well defined on the boundary. And suppose you know that the gradient of the function is vanishing on a boundary set of positive area. Does it imply that the gradient is zero everywhere? Oh, this is a question that we don't know how to answer. And there are several cases when it's true, and even these cases are quite useful. So if S is a relatively open subset of the boundary, then the answer is yes. And we use this statement in the proof of lower bound in Yau's conjecture. But we cannot answer this question in the case when we have some kind of wild boundary set of positive area. And also in dimension 2, in dimension 2, this question has positive answer due to connection with complex analysis. And there was some unexpected, very unexpected turn in this question. Thomas Wolff constructed a counterexample to this question, which was C1 epsilon smooth up to the boundary. And it's quite sad, but we still have some hope that it's true if we assume additional smoothness of the function up to the boundary. Okay, so this was our brief story about Howey dimensions. Now we will come to a very beautiful idea of Nadirashvili in 2 dimensions. So Nadirashvili tried to attack Yau's conjecture in 2 dimensions using quasi-conformal mappings. And it appeared that it worked not as quite as we expect. So we cannot, for the moment, we cannot, this trick is very beautiful, but we cannot prove the Yau's conjecture even in dimension 2, so there are a lot of nice tools there. But I will tell you some application of this trick which works in another problem, and I think it's really beautiful trick. So let me tell you about it. So on the scale 1 over square root of lambda case, some scale small constant c over square root of lambda, Laplace eigenfunctions, they behave like harmonic functions. And there is a mathematical statement to justify it. So Nadirashvili observed that you can make some sort of change of coordinates in the ball of radius c over square root of lambda such that the zero set of eigenfunction becomes the zero set of harmonic function. And this change of coordinates is quite tricky. It actually is not explicit. Moreover, it depends on the function phi itself, but it has like good quantitative estimates how bad is the change of the coordinates. Nazarov, Poltarovich, and Sorin, they were developing the ideas of Nadirashvili, and they proved very nice bounds for a symmetry of the zero set. We were trying for a long time to apply unique continuation to zero sets of Laplace eigenfunction, and it appeared that there is an inverse connection here. You can actually apply zero sets to unique continuation. There is a statement, a question about elliptic PDE where there are no zero sets, but you use them in the proof, and their trick of Nadirashvili is working. Okay, it will be a little bit technical. So there are 3 steps in the idea of Nadirashvili. I will just skip it and go immediately to applications. Okay, here is the application. So suppose you have a solution of the Schrödinger equation in R2. So the function u is defined on the whole plane. And V is a bounded potential. And Landis asked how fast the solution of the Schrödinger equation can decay near infinity, and it conjectured that if u decays faster than exponentially, then u should be identically zero. You can construct an example of the function which satisfies the Schrödinger equation with some bounded potential v, but decays exponentially fast. So if you take the function e to the minus x, so there is a little problem with this function. It is not very smooth near the origin, but outside of the unit ball, it's satisfied this inequality with uniform constant c. And you can actually make it a little bit smoother near the origin, and it will give you an example of solution which decays exponentially. But Landis conjectured that any such solution cannot decay faster than this in example, cannot decay faster than exponentially. And then there was a counterexample by Meshkov. Meshkov told us that the Landis conjecture is false, and he actually constructed an example of the function with decays like e to the power minus x to the power 4/3, which is faster than exponentially. And he also showed that if it decays faster than with the power 4/3, then it should be identically zero. But this counterexample, it has a complex valued solution, and probably the Landis question was about real valued solutions. For most of the applications, I think that the case when v and u are real is quite interesting. And so let's now assume that u and v are real, and it appeared that this conjecture is true for real potentials, and this beautiful idea of Nadirashvili, how to apply quasi-conformal to mappings to zero sets, it didn't work for Yau's conjectures quite well, but it appeared that you can apply quasi-conformal mappings and zero sets to unique continuation problems. It appeared that quasi-conformal mappings and zero sets are very friendly. So the proof is using zero sets. I think this is the first really nice application of zero sets to unique continuation properties. Related to Laplace eigenfunctions, okay, so we had some suspicions about Laplace eigenfunctions. Let me mention first one observation about real valued solutions to differential equalities. Suppose we have a Riemannian surface and we have a real valued function u such that lambda of u is smaller than lambda times u. It appears that the vanishing order of any such solution is smaller than lambda to the power 1/2 plus epsilon. And we have suspicions that probably in the Yau conjecture, you don't have to work with Laplace eigenfunctions. Probably there are good estimates for the length of zero set of solutions of differential inequalities. But these are only our suspicions. We only don't know, but we are quite impressed by the power of Nadirashvili's tricks that goes 30 years ago, but after 30 years, it looks like brilliantly applicable to some questions on unique continuation. Thank you. Yes, so it's very related. So I think that Koenig and a number of his students, they were trying to apply quasi-conformal mappings following the Nadirashvilis. And I think that finally we understand how to apply quasi-conformal mappings. And the key new ingredient here is to combine zero sets and quasi-conformal mappings. Yeah, thank you for the comment. Yeah, for complex valued solutions, we actually don't have, we don't see zero sets. For real valued, if you know that something weird is happening, like function is growing very fast or decaying fast, there should be a lot of zero sets. And that distinguishes the real valued case and the complex valued case.